Now let's take a look at periodic trends in the properties of elements. And what we mean by periodic trends are predictable trends based on an element's placement on the periodic table. Now we're just going to be focusing on the main group elements, which we remember are the S and the P block. Let's take a look first at atomic size. And when we're talking about atomic size, we're looking at the volume or the radius. We're going to treat atoms as marbles or billiard balls, and so their volume is directly proportional to the radius. The first trend we're going to look at is as we go down a column. As we go down a column, the size of our atom increases. And that's because as we go down a column, we are increasing the energy level that's being filled. And we know that as we go up in energy level, those subshells are further away from the nucleus, which means our atom is going to be larger. So lithium, we're filling our second energy level, or the subshells in the second energy level. And potassium, we're filling subshells in the fourth energy level. And the difference between our energy level is as our energy level goes up, further from the nucleus. So as we go down, our atomic radius or volume is going to get larger. Now, as we go from left to right, the size of the atom decreases. So let's take a look. If we look at our second period, lithium, beryllium, boron to neon, the number of electrons increases. Why does the size go down? Well, also as we go from left to right, the number of protons is increasing as well. In lithium, we have 3 protons, which means we have a nuclear charge of +3. Neon, we have 10 protons, which means the nucleus has a charge of +10. As we go from left to right, all of our electrons are going in the same subshell, S and P subshell, but the nuclear charge is increasing, and that increased nuclear charge pulls the electrons closer to it. So as we go from left to right in our main group elements, our size decreases. In a given period, the alkali metal is always going to be the largest, and the noble gas is always going to be the smallest. So pause the slide and see if you can correctly identify which is going to be the larger atom in each pair. Whoops. Okay, so let's take a look. Here's carbon and here's oxygen. They're in the same period, and as the atomic number goes up, the size goes down. Carbon has a nuclear charge of 6, oxygen has a higher nuclear charge of 8, so oxygen is going to be smaller, carbon is the larger atom. Lithium or potassium. Lithium is filling up the second energy level, potassium the fourth. Potassium is going to be larger. Carbon or aluminum. Aluminum is in a different period, but it's in the third period, which means it's going to be larger, and it is to the left of carbon, which means it's going to be larger. What about selenium or iodide? Well, here we have opposing trends, so it's hard to figure out. If we look at iodine, it is 1 period below, so it should be larger, but it's to the right, which means it's smaller. So in this case, we really can't tell. If we look at this pictorial representation, again, it's very hard to tell. So when you have opposing trends, we really can't predict. Okay, now let's look at a periodic trend known as ionization energy. Ionization energy is the minimum energy needed to remove an electron from an atom in its gaseous state. This is always an endothermic process. We've got to add energy to pull that electron away because the positively charged nucleus is holding those negatively charged electrons on the atom. So to pull an electron away, we've got to overcome the nuclear charge. Valence electrons are always going to be the easiest to remove. So if we look at some element, this is what is happening in the ionization energy. We have some element in a gaseous state. It's always going to be an atom, even if it's even if it's one of our Brinkelhoff elements. When we're talking about ionization energy, it's always going to be an atom in the gaseous state, which, by the way, except for the noble gases, is an artificial condition. Okay, so we have an element in its gaseous state. We add the ionization energy, and when we do that, we remove an electron. Our electron becomes a product, and our element has a positive 1 charge because it's lost an electron. And we can keep on adding energy and energy and remove all the electrons. Let's look at the second ionization energy. Here we have our atom. Well, it's now an ion, a cation with a positive 1 charge. If we add more energy to it, we can remove a second electron, which becomes a product. And now our atom, or actually our ion, has a +2 charge because now it's lost a total of 2 electrons. The third ionization energy would remove another electron, and a resulting cation would have a +3 charge. So whatever ionization energy we're looking at, that's going to be the positive charge of the cation that we form. And it's always going to be a positive charge because we're removing an electron. Now again, this is an artificial condition. This is something that must be done in the lab. Most, except for the noble gases, nothing exists as an atom in the gaseous state. So this is an artificial condition, but it gives us some important information about electrons. The ionization trend is exactly opposite that of the size. The larger the atom, the easier it is to remove an electron, because that electron is further from the nuclear pole. So as we go down a family, our ionization energy goes down because our size goes up. The ionization energy trend is exactly opposite that of the atomic size. So as we go down a column, the ionization energy gets smaller because our electrons are further from the nucleus. Now, as we go from left to right, our atoms get smaller. So that means our electrons are being held much more tightly by the nucleus, and it's going to be harder to remove them. So as our size goes down, our ionization energy goes up. We need more energy to take electrons away from smaller atoms. So as you go from left to right, the ionization energy gets larger because that nuclear charge that electrons feel increases. So if you can remember the size trends, the ionization energy trends are exactly opposite. Now, if we're looking at a given element and looking at its ionization energy, as we take electrons away, it becomes harder and harder to remove them. So the first ionization energy is always the smallest. Then the second ionization energy is always larger. The third ionization energy is always larger until you remove all the electrons. And this trend right here is for one given element. It's always easiest to remove the first one, second one's harder, third one's harder, etc. So here are the trends in ionization energy, opposite those of atomic size. As we go from left to right in our main group elements, our ionization energy increases. We need to add more energy to take electrons away from a smaller atom. And as we go down, our ionization energy decreases. As our atomic size gets larger, it's easier to remove an electron. We don't have to add as much energy. So pause the slide and see if you can choose the atom with the highest ionization energy. And we mean the highest first ionization energy from each pair. Okay, so let's look at magnesium and phosphorus, both in the third period. Phosphorus is smaller than magnesium, so it's going to have the larger ionization energy. Harder to pull an electron off from phosphorus than magnesium. Chlorine or bromine. Bromine is larger than chlorine, so it's going to be harder to take an electron off chlorine. Chlorine will have the larger ionization energy. selenium or antimony. We have elements in two different periods, but antimony is larger. So therefore, selenium is larger in size, So therefore, selenium will have the larger first ionization energy. It's smaller, takes more energy to remove those electrons. But if we look at phosphorus and selenium, they have opposing trends, so we can't predict. The last type of trend we're going to look at is what's known as metallic character. How much like a metal is a given element? We know that metals are malleable and ductile as elemental solids. They have luster, they conduct heat and electricity, and in terms of their chemical properties, they form oxides and basic solutions. They always form cations. They lose electrons when they react. They always get oxidized. Nonmetals are brittle in the solid state, non-reflective, insulators. Their oxides are acidic. They form anions and polyatomic anions, and when they react, they either share or electrons or gain electrons. So on the left-hand side of the periodic table, we have metallic character, and as we go down, our elements become more metallic. So the metallic character follows the trends for atomic size. The larger an atom is, the more metallic it is, because its electrons are further away, easier to move around, which characterizes the properties of metals. So metallic character follows the trend for size. As we go from left to right, our metallic character decreases, just like size decreases, and as we go down, our metallic character increases. So this is going to be the most metallic, the least metallic. So if we look at which element is going to be more metallic, tin or tellurium, it's going to be tin. Tin is to the left of tellurium, it's larger, therefore more metallic. Phosphorus or antimony. Here's antimony, here's phosphorus. Antimony is larger, therefore more metallic. Germanium or indium. Here's indium, larger in size, more metallic. Sulfur or bromine, we have opposing trends, and therefore we can't predict. Whoops, out of order. Okay,